All right, I had a student who requested that I would do a problem regarding empirical and molecular formula writing, and I'm trying to help that student out, so I'm recording myself doing that. All right, and first of all, let's talk about empirical formula, right? So empirical formula versus a molecular formula. The empirical formula is the smallest ratio between the atoms. So this would be something like NaCl, where you have one sodium for one chlorine. The molecular formula is also NaCl. Now something we need to note about that, right, is that if you have an ionic compound, that will always be the case. But sometimes we might have something like this, where, you know, we have C6H12O6 glucose molecule, right? Well, we can divide a 6 into each of those, so the smaller or empirical formula of CH2O would exist. And so we have a process that we can go through that allows us to use some of the stoichiometry stuff we've done, namely being able to turn things into moles, and being able to figure out different types of formulas, namely empirical and molecular formulas. So here we go. I'm going to do a problem right off of one of the pages we have here. It's one of the harder ones. So it says if you have 83.625 grams of carbon and you have 16.375 grams of hydrogen, what are the empirical and molecular formulas? Step number one for the empirical formula, which you have to do first, is to turn it into moles. In order to do that, you divide by the molar mass of the object, which is carbon, which is 12.01. You do the math on that, and you get 6.963. Here, 16.375 divided by 1.01, which is the molar mass of hydrogen. You do the math on that, and you get 16.21. Now, here's the next step. The next step is you look at these two numbers, they're moles, and you divide by the smaller one. Well, in this case, 6.963 is smaller. Again, 6.963 is smaller. When you do that, you get a 1. When you do this, you get 2.33. Now, you got a little bit of a problem here because I've never seen a chemical formula, and you never will, where it's C1H, 2 1/3, right? That doesn't exist due to John Dalton's laws. So John Dalton says you have to have simple whole number ratios, and that's how they combine and make these things called chemical, compounds. So what we have to do is we have to say, okay, what can we multiply this by to get a whole number? Well, what we can do is we multiply by 3. Gives us 1 times 3 is 3, 2.33 times 3 is 7. Therefore, that's what these little 3 dots means, the formula would be C3H7. Now in this problem, I furthermore go on to tell you that this thing has a molecular weight, which we're going to call a GMM, that is equivalent to 388.78 grams. Now, when you do the molecular formula, you take the mass of this, so it would be 3 times 12.01 plus 7 times 1.01. And that GFM is what we call it, ends up being, I'm going to cheat and look here, 43.1. All right, we'll go 43.10 because we always go to the 100th place in class. Now, molecular formula says you take the GMM and you divide by the GFM. So what you do is take 388.78 divided by 43.10. When you do the math on that, you end up getting the number of 9. Now, what does that mean? What it means is this. Remember I told you there's that whole, C6H12O6, which was 6 times bigger than CH2O, right? Well, this means that the molecular form is going to be 9 times bigger than this one right here that was the empirical. So 3 times 9 is 27, therefore C27. For H, 7 times 9 is 63. So H63. That's your molecular. So your two formulas are here and there. Hopefully, those of you watching will benefit from me doing that particular problem. Bye.